Hi, welcome back to my channel Fusion Sphere. Today we're going to be covering a topic of aerodynamic, which is the theory of lift. What makes an aircraft fly? I have always been intrigued by this question since I was young. So some of the principles that surrounds the theory of lift and more in detail what makes an aircraft fly, what generates lift on any surface. So that's the topic for today. So when you're talking about theory of lift, we're referring to the lift in terms of Bernoulli's principle. What is Bernoulli's principle? Let's recap quickly with the formula. Here we have the Bernoulli's principle. An equation is given as static pressure plus dynamic pressure will give you the total pressure. So in terms of how it works, the Bernoulli's principle states that the airflow that is coming over the airfoil, let's say this one, red, is going to be much faster than the airflow that is on the bottom and given in green. The velocity of airflow above the airfoil is faster because it have a longer distance to cover, in contrast to the airflow below the airfoil in green has a lower speed. So according to Bernoulli's principle, the pressure difference caused by the difference in the distance traveled by the airflow above and below the wing is what generates lift. The high velocity of air creates a region of lower pressure on the top and vice versa. If that's the case, then let's take a look at this example. This could be considered as an airflow upside down. According to Bernoulli's principle, we would expect a region of lower pressure on the bottom, which is region 1, and a higher pressure on the top, which is region 2. But that's not the case here. To understand what's happening here, let's take a look at the Coanda effect. The Coanda effect explains how here we have a region with higher pressure despite the fact that the airflow below the surface has a much longer distance to cover. If you were to consider this distance versus this distance, which is basically a flat surface, as you can see here. The higher pressure region below the airfoil is created due to the effect of centrifugal force that is experienced by the airflow. A quick recap on what is centrifugal force. Here's an example. As the car is making a turn, it experiences a centrifugal force outward, and what is balancing that force is centripetal force. Similarly, in this case, as the airflow follows the curvature of the airfoil, the bigger the curvature, the faster the speed of flow, which in result, we have a higher centrifugal force outward for the airflow. And what is balancing the centrifugal force in this case is atmospheric pressure. So here, looking at the bottom region, the farther we go away from the airfoil, the streamline is more straight compared to the streamline much closer to the surface. So closer to the surface, the streamline has a higher curvature, which means a higher velocity of air. In result, we have a higher volume of air that is hitting the surface. This is creating a region of higher pressure closer to the surface, contrast to right here. One way to look at this would be to consider the area that is under the streamline closer to the surface of the airfoil and another region somewhere farther away from the airfoil where the streamline is relatively straight. The same principle could be applied over the airfoil to understand the concept behind why it is a low pressure region. This basically covers how lift is generated in terms of Coanda effect, that the airflow wishes to reach an equilibrium point to satisfy the conservation of energy, thus flowing from a higher region to a lower region of pressure. This more in detail explains how the pressure varies in altitude and in a specific location around the airfoil. A point to note is that the physics of pressure closer to the wing surface cannot be applied to a free surface, like a free space. For example, the pressure gradient above sea level. So if you are to look over here, let's consider like this region right here to be the sea level, and as we increase in altitude, we see that there is a decrease in pressure. The red represent the intensity or the gradient of pressure. So we have a higher pressure here, which would be the sea level, and we have a much lower pressure in higher altitude. Now, taking a closer look at how air flows over the wing, here we have the stagnation point, where you're going to have the separation of airflow, one portion that would go over the wing, and the other would be going below the wing. Here is a better example of a boundary layer. So closer to the surface, the velocity of the flow is not fully developed. We only experience the velocity of the flow to be fully developed around this region, which result in the average flow, average velocity of the flow, but right here, midway. Now to summarize, we have compared Bernoulli's principle versus Coanda effect. The Bernoulli's assumption is that at the stagnation point where the flow of air separates the airflow from the leading edge of the wing must meet at the trailing edge, covering a longer distance over the top of the airfoil is what creating a region of low pressure, and you get a higher pressure on the bottom. In terms of Coanda effect, it states that respecting the law of conservation of energy, the air moves from a high to a low pressure area, and the pressure difference, which is the atmospheric pressure, is due to the Coanda effect um, in terms of centrifugal force that is experienced by the airflow. That's all for now. Thank you for watching. Until next time.